Hello class, welcome everybody from the beautiful Hilton Garden Inn in Champaign, Illinois. This is torsional displacement of circular shafts, and basically what we're looking at is how much does a shaft twist when you put a torque on it. All right, so the classic example is down here in the lower left, a truck drive shaft or any kind of drive shaft for a vehicle. We're going to have a torque on that, and it's going to twist a little bit. Typically, if it's something pretty stiff like steel or something like that, it's not going to twist that much. But we can use shearing strain, we can use Hooke's law for torsion, we can use these relationships that we know to figure out how much it will actually twist. Another interesting application of this is the drive shaft for a lift fan up here in the upper right. This is a gas turbine engine. And this right here is called a lift fan, or the lift fan on the F-35. The F-35 can hover, and the point of the lift fan is to enable that hover. So the drive shaft between the gas turbine and the lift fan is how the gas turbine is able to drive that fan. And the fan draws air in from the top and it blows it out the bottom in order to enable that hovering capability. So we'll talk about that more later in I should say in a couple different lessons, because the lift fan actually has some interesting power transmission things involved with it too, and so that'll be coming later. So let's continue. There's several similarities between axial loading and torsional loading problems that are worth noting. So basically, what we're going to do in this lesson is we're going to say, if I've got an axial loading problem here, like P, we know that the stress is going to be equal to the elastic modulus times the strain. By the way, I know that it's kind of annoying how the pen makes noise on the microphone. I don't really know any way around that, but I'm sorry for all the pen writing on the screen noises that you hear through the microphone. The stress in this case is P over A, and putting these things together with each other, we can come up with what the overall deflection of this thing is going to be: P L over A E. Right? Now, something very similar can be done with a shaft that has a torque on it. So if I've got torque acting on, whoops, let me get rid of that, kind of going the wrong direction there. If I've got a torque acting on a shaft like this, what I want to know is how much does this thing twist with respect to the other side. And basically, I have analogous expressions. I can say my shear stress is equal to my shear modulus times my shear strain. I can say my shear stress kind of at the outer edge is going to be the torque times C over J. It's important to note that C is usually the variable we use for the outer radius of the shaft. J is the variable that we use for the polar moment of inertia. And we'll talk about that a little bit more in a few minutes. You've seen moments of inertia a bit in 202. We're going to use them quite a bit in this class. Anyway, putting these two equations together, we can come up with what the theta value is, what the twist is, and it looks a heck of a lot like the expression for axial displacement. All right, it just has rotational things and shear things instead of axial things and normal stresses. So let's continue and see how we put that together. Now, to put together the angle of twist, we're going to have to look at shearing strain along the length of the shaft. So shearing strain varies along the length of the shaft, and it varies with radial position within the shaft. So I'm going to draw a diagram here, but then I'm going to use our swim noodle to look at it in a little bit different way than we have before. So this is our torque, like this. And imagine drawing a line across it, like this. All right? And if I put that torque on there, then that line is going to deflect like this. And it turns out that deflection there is our shearing strain. All right, and just to illustrate that a little bit, we've got the swim noodle here. All right, so we've had this in class before, and if you take a look at this dashed line right here, and I twist this thing, that dashed line deflects around, right? And so on this end over here, that dashed line, is down. On the other end, it's up. And basically, we just want to know what is the angle that thing's making, because the angle that thing's making is going to give us an idea of how much deflection we have. So let's look at this. This angle is the theta, the twist angle that we're interested in, right? And if we have a radius of c, then this distance, let me actually change the color here. This distance right here is going to be approximately c times theta. And if this length of this whole thing is L, then I can say that my shear strain, I should say the tangent of gamma, is going to be c theta over L. All right? For small angles, we can say gamma is just equal to c theta over L. Right? And this is definitely going to be a small angle, because in general, we're not talking about things that twist as much as this, where you can actually see a huge twist angle like that. Typically, we're talking about steel or something stiffer that you really can't see the twist. All right, so the angles are going to be very, very small. One thing that's important to notice here, however, and this is related to this rho, radial distance from the center. We can write shear strain as c times theta over L, like we've done that, but we're also going to define, instead of just this c as the radius, we're also going to define a radial position, which will just be rho. So any radial position within the interior of the shaft we'll define as rho, and then we can say that we've got a shear strain at that radius, shear rho, I should say gamma rho, as rho theta over L. All right. So that's those are two different quantities, and they're both going to be important in just a minute here. So let's continue. If we stay below the proportional limit, we can use Hooke's law for torsion. All right, the proportional limit is basically the limit at which stress and strain are linearly related. And in this case, we're talking about shear stress and shear strain. So it's just the limit below which we've got a linear relationship between tau and gamma. All right. If we do that, then we can use Hooke's law, and the next thing we need to do is relate torque to shear stress. And I want to explain what this box, or I should say this circle here is with the gray color in there. Basically, what that is if we have a shaft that looks like this, we've got a torque on it, all right, and I'm gonna make a slice through there and open up the inside of it such that we can see something that looks like this. So I've got a slice on it like this, and here is the torque. Now that torque has to be resisted by something, and just because I sliced it doesn't mean that this thing isn't still in equilibrium. right? That torque is resisted by shear stresses that are acting on the inside surface of that, right? Basically on the interior material in there. So the shear stress on that face resists the torque, right? And basically that's what we're going to quantify with this figure right there. So we've got a shear stress acting over that whole thing, and we want to integrate over the whole face so that we get the total torque, right? So we're going to say that the shear stress acting on that ring at radius rho is just tau rho, okay? And what we're going to do then is sum that all up so that we can estimate what the torque is. So the total torque is going to be the sum over that whole area, I should say the integral over that whole area of tau rho times dA. That's going to give us a that's actually only going to give us a force, right? Because this is a stress, and this is an area. So we also have to multiply by a rho in order to get a moment arm, right? So all of those things together will give us a torque. And if we integrate over that whole face that we see there, then we'll get the total torque as it relates to the shear stress. The area, you see right here, we've got a little dA. The area of that little band, that little ring in there, is just going to be the circumference of that ring times the thickness of the ring. Right? So we can estimate the area as the circumference of that thing times the thickness of the ring. And the ring is infinitesimally thin. It's d rho in thickness, and so this makes a good approximation for our integral. All right. So there's a couple of things we're going to have, a couple of relationships we're going to have to figure out in order to take the next step. But let's do that now. All right. In order to make more sense of this integral, we really want to change what we've got here, tau rho. All right. In order to change that, we're going to make use of some of the relationships that we've had on the previous pages. So we've got a couple of them here. We can say, recall that gamma rho was equal to the radial position rho times theta over L. We could also write something that looks like gamma C, which is basically just the shear stress at the outer radius. That's going to be C times theta over L, right? And we can make a relationship there, or I should say we can combine a couple of things here. Also recall the shear stress at the outer. Well, actually, let's not write it that way. Let's write the shear stress at a position rho is going to be equal to the shear modulus times the shear strain at a position rho. The shear stress at the outer surface is tau C times shear modulus times the shear strain at the outer radius C. All right, and if we put all these things together, I should say we put these relationships together, we can write that tau rho over rho is equal to tau C over C. And basically then we can say that tau rho is just going to be rho over C times tau C. And it's going to turn out that that's a more useful expression, because basically tau c is a constant, right, with radial position r, and that's going to be more useful for this integral. So let's put that into this integral. It's going to be more useful because we can actually then take it out of the integral, and we'll just have rho in the integral instead of tau rho, which is a function of rho. All right, so let's put that in the integral. It's going to end up looking like rho times rho over c tau c dA. All right, and the tau c over c is a constant, so it can come out. And what we're left with in the integral is going to be rho squared dA. All right, and that rho squared dA is equal to J, which is the polar moment of inertia. All right, so we now have several different relationships, and we're going to put them all together on the next slide. If we collect the relationships we have, we can put them together such that we can get theta as a function of torque. So theta is twist. We want that as a function of the torque. So let's take this equation and solve it for theta. So that's going to give us gamma rho times L over rho. We'll put that together with this one. So the two of those will give us. Basically, we're going to replace the gamma rho there with tau rho over g, and that's multiplied by L over rho, and then we'll replace that tau rho in that equation with something that's got torque in it. So now we'll say theta is equal to rho times torque over J times L over G rho. So our expression for theta, if we cancel out those rho's, we're going to have T, and make a better T there. We're going to have torque times the length over JG. And that expression there is what we had on the first page when we were just introducing it. But that expression relates the twist of some circular shaft as a function of the torque. Okay, let's do an example now for a steel shaft that's connected to basically a rigid wall right there. It's got a torque acting on it. But there's a bunch of different things that we can calculate given all the different relationships that we have. So let's find the maximum shearing stress in the shaft. And basically that's going to be the shear stress at the outer radius, all right? Tau c. And that's going to be equal to that outer radius c times the torque over J, right? And we know that's where the maximum shearing stress is because anywhere else, that c, the c right there that I'm marking, that c would be a rho if it's somewhere on the interior surface, and it would then give us less shear stress. So the maximum shear stress occurs on the outer surface. We're going to have to calculate the polar moment of inertia for this, that J value. J, you can, how to find J for various shapes. You can either do that integral that we just showed earlier, or you can look it up. It's one of those things that's in your 202 book. I It's in just about any textbook, or even if you Google it, I'm sure you can find a polar moment of inertia for various kinds of shapes. For a circular shape, actually for a hollow circular shape, it's going to look like pi over 2 times the outer radius to the fourth minus the inner radius to the fourth. All right, and that's going to be, in this case, pi over 2 times, we've got the outer radius is going to be 0.2 meters squared. The inner radius is going to be 0.15 meters squared. I'm sorry, that's not squared, that's to the fourth. I'm sorry, 0.2 to the fourth, 0.15 to the fourth. That's going to give us 1718 times 10 to the minus 6th meters to the fourth. All right, let's put that into our expression for tau c, and we get c times torque over j. That's going to be, c is the outer radius, so that's 0.2 meters. The torque in this case is 300 times 10 to the third Newton meters. Divide all of that by 1718 times 10 to the minus 6th meters to the fourth, and we get 30, that's supposed to be a 3, 34.9 times 10 to the minus 6th newtons per meter squared. I'm sorry, that's not 10 to the minus 6th, that's 10 to the 6th. So that's going to be 34.9 megapascals. All right, the shearing stress on the inside surface of the shaft is basically just going to be that similar expression for shear stress, except we're going to use a different radius. So on the inside surface, we use tau rho equals rho times torque over j. And in this case, the rho is the inside surface radius, which is 0.15 meters. Again, we got the same torque as before, 300 times 10 to the third Newton meters, divided by the same polar moment of inertia, 1718 times 10 to the minus 6 meters to the fourth. That's going to give us 26.2 megapascals. All right, so the outer radius stress is 34.9, the inner radius stress is 26.2. And the last thing we're supposed to find is the angle of twist. It's part C. The angle of twist in a 2 meter length of the shaft. So that's going to look like theta equals T times L over JG. That's the torque, 300 times 10 to the third Newton meters. Our length, we're told, is 2 meters. We still have the same polar moment of inertia. That's 1718 times 10 to the minus 6th meters to the fourth. And our G, we were given 80 gigapascals as our shear modulus. So that's going to look like 80 times 10 to the 9th pascals. And if we do that math, we're going to get 0.0044. And that would be radians, right? So, so the expression like this, if we take a look at the units, we better get units that cancel out into nothing, right? And nothing is basically radians, right? So let's just take a look at the take a look at the units here. In the numerator, we're going to have newtons times meters squared. In the denominator, we have meters to the fourth times a Newton per meter squared. That's what pascals are. And it looks like our newtons cancel out. And it looks like, yeah, that will cancel out for the meters as well. And we end up with radians. Right? Remember, radians are basically dimensionless. Okay, so that's our answer then. That's not much deflection, but that's because it's a steel shaft, so it didn't rotate very much, or didn't twist very much. Now we've got an example that's a little bit more complicated. Basically, we've got a motor, and it's supplying torque to a shaft that's connected with a bunch of gears, right? And we're told what the torque of the motor is. We're told what that it's a steel shaft on there, so we've got a shear modulus there of 80 gigapascals. There's 3 machines that are driven by all those gears, B, C, and D, and they require different amounts of torque each in order to run. And so what we want is the minimum diameter required if the maximum shearing stress in the shaft is limited to 100 megapascals, right? And then part D just says what's the rotation of gear D with respect to the coupling at A if the coupling in gears are spaced at 2-meter intervals and the shaft diameter is 75 millimeters. So let's start with that first one. Basically, what we're going to have to do is a free body diagram, and a free body diagram that looks a little bit different than what we've done in the past. So, I mean, what we've done in the past is typically not involve torques. So let's start part A by doing a free body diagram of this thing. Right, and I've got the motor over here at A delivering what we're told is 5.5 kilonewton meters of torque, right? And at B and C and D, I've got different amounts of torque. So at B, there's a motor that requires 3 kilonewton meters. At C, there's one that requires 1.5 kilonewton meters. And at D, I've got one that requires 1.0 kilonewton meters, right? And in order to do the analysis properly, we need to know what is the torque at any given location on the shaft, all right? And just by looking at these torques right here, it's not necessarily super clear, right? So what we're going to have to do is basically slice this shaft like this, so that we find the torque acting on this zone here between A and B. So I'll just say to find the torque acting on shaft AB. All right. So let's draw then a free body diagram of just that slice, right? And that's going to look like this. Here's that sliced area. So I've got the 5.5 kilonewton meters here, and I'm going to have some torque acting here, which then I can say the sum of the moments about this thing has to be 0. So TAB plus 5.5 kilonewton meters equals 0. So then that means that TAB equals negative 5.5 kilonewton meters. And the fact that it's negative just means that I defined positive in the direction that I drew it there, and it came out the opposite way. So for TBC, we're going to slice the shaft in between gear B and gear C. So that's going to look something like this. I'll just draw this a little bit bigger. Now I've got a slice here, and in this case I've got 5.5 kilonewton meters. I've also got 3 kilonewton meters. That was the torque at B, and then where I sliced it, I'm going to call that the torque at BC, or basically the torque that's acting on the shaft in between B and C. If I do sum of the moments is equal to 0, I'm going to get 5.5 kilonewton meters minus 3 kilonewton meters plus TBC equals 0. So then that means that TBC is equal to negative 2.5 kilonewton meters. Right? And if I did the same thing, for the torque at C and D, I would end up with negative 1 kilonewton meters for the torque there. So we can summarize that with a drawing that looks like this. So here's X, here's the torque, and I can say, along the length of the shaft, we've got A, B, C, D like this, and in between A and B, I've got a moment of negative 5.5 kilonewton meters. Let me put units on here of kilonewton meters. All right, and in between B and C, I've got a torque of negative 2.5, and in between C and D, like this, I've got negative 1.0. Right, and what that tells me is now I know that in between A and B is going to be my maximum torque. So this right here is the maximum torque on the shaft. And I can use that now to find the maximum shearing stress, because that's what was asked for, right? The question is asking for I shouldn't say it's asking for the max shearing stress, but it's basically asking for the diameter that's required if we want to limit the maximum shearing stress in the shaft to 100 megapascals, right? So let's put that together with basically with an equation so that we can solve for that diameter. So what is that going to look like? We're going to have tau max is basically going to be that expression that we've been using for tau C. The shear stress is the maximum on at the outer radius. Tau C is going to be C times torque over J, right? And basically we know everything in this expression except what the diameter is, right? So we want the diameter such that tau max is 100 megapascals. All right. So let's rearrange this equation so that we can put some diameters in there so that we can solve for that. So tau max, we can replace that that radius C with a diameter over 2, and we've got a torque here we know what our max torque is. The polar moment of inertia, if we're writing it in terms of diameter, and then it's a solid shaft, it's going to be pi over 32 times d to the fourth. All right. So let's put those. Let's rearrange that a little bit so that we simplify it a little bit. Just getting rid of the 2 and the 32, and we'll cancel one of the d's. So we'll end up with 16 times the max torque over pi d to the third. All right. So then solve for d. That's going to be the cube root of 16 over pi max torque over max shear stress. All right, if we put some of our numbers in there, we've got 16 over pi. Our max torque is going to be 5.5 times 10 to the third Newton meters, and our maximum shearing stress is 100 times 10 to the 6 pascals. That's going to give us 0.0654 meters, or 65.4 millimeters. All right. So here's a question: is this value here, is that the maximum value or the minimum value of d? All right. I'll let you think about that a little bit. All right, but basically, it's the minimum value, because if d gets any larger, and I don't know if you can picture this, but try to picture this. If d gets any larger, then the maximum shear stress is actually going to get smaller, right? And that would be a good thing, right? If the diameter gets smaller and smaller and smaller, imagine that all of that torque has to be supported by a smaller and smaller radius, and so the shear stress is going to get even bigger, right? So this value that we've just come up with is the minimum value. You have to have at least that diameter in order to limit your stress to 100 megapascals. All right. Now the next part, where they're asking us to find the angle of twist between A and D, that's actually going to be a summation, a little bit like the wedding cake problems that we've done in axial deformation, right? In axial loading, right? In this case, we're going to have a summation. I'll say a summation from 1 to n of some torque, some length, some g, some j, right? Because in each of the lengths of the shaft, we can have a different torque, a different length, a different g, a different j, and essentially what that's going to look like is something like this. The deflection, the twist from D to A is going to be the the twist from B to A plus the twist from C to B plus the twist from D to C. Right, so that's going to look like the torque AB times the length over GJ. L, G, and J are the same for all three of our sections here, so really the only thing that's changing is the torque. So I'll just pull the LGJ out to the front, and I'll have torque AB plus torque BC plus torque CD. All right, and if we put all of those together, we've got 2 meters for our length. Our shear modulus is 80 times 10 to the 9th pascals. Our J is going to be computed from the 75 millimeters that we were given. That's going to be pi over 32 times 0.075 meters to the 4th. All right, and we'll multiply that by negative 5.5 times 10 to the 3rd Newton meters, minus 2.5 times 10 to the 3rd, minus 1.0 times 10 to the negative, or 10 to the 3rd. All of those are Newton meters, and we end up with 7.2 times 10 to the minus 2 radians, which is going to give us just 0.072 radians. All right, and that is how we can find the twist in a shaft that's got, changing torques along its length. So let me know if you have any questions about this. This lesson should be all that you need for finishing the homework for Friday.